Lastly, we talked about, I think, was extracting elements from matrices. So we're going to continue to build on some foundational stuff, and then in the next section we'll actually start doing more operations on matrices and finding out more interesting things about them. So the next thing to talk about after talking about extracting elements is partitioning a matrix. So sometimes it's convenient that if you have a matrix, a big matrix, and then you look at it closely, there are parts of the matrix that look like there are some patterns going on. So in a situation like that, you might be good to what's called partition a matrix, and that is to cut up the matrix into sub-matrices, they would call them, and they don't all have to necessarily be the same size, but we can look at them as matrices that are simpler to deal with. So, for example, in this particular matrix, this is a 1, 2, 3, 4, 5. This is a 5 by 2, 3, 4, 5, 5 by 5 matrix. But if you focus on the first 3 by 3, that looks like an identity matrix. And then if you focus down below, a bunch of zeros. So it might be appropriate to cut up the matrix into 4 sub-matrices, where the first block is an identity matrix. The rectangular matrix below that are a bunch of zeros, and then you just have a B and C. So if you do any operations that might require you to multiply things out, for example, then you might have an easier chance of multiplication. So there was an example that I'd like to do. It's not until down here somewhere. That would aid in our multiplication a little bit if we think about dividing up this matrix. So here they show you how to divide the matrix already, but we can assume that we didn't know how to divide it, or that we could. We can assume that we have a 2 by 4 matrix here. And then we want to multiply this with B, which is a 4 by 3 matrix. And so we should expect this to, our result to be a what by what? We should expect this to be a 2 by 3 matrix at the end, right? So what we could do, let me go about a longer way of doing this first, and then we'll see if we can find a shortcut. But a longer way of thinking about doing this is to actually do the matrix multiplication. So we would do this row and then this column to get our first element. So that row, we have 2 times 0, 3 times 0, 1 times 1, and 0 times 2. So that looks like it's just going to be a 1. And then we stay on the first row, and then we go to the second column. 2, 0, 5, that makes 7, so 7. And then I think there's one more column on that first row. So we do a 2 times 0, 3 plus 4, and 0. 3 plus 4 is 7. All right? So this wasn't so bad, I suppose. Now if we look at the second row, this is our last row here, because we know that we only have a 2 by 3. So the last row will be 4 times 0, 5 times 0, 0 times 1, and then negative 2. Let's move over to the next column. 4, 0, 0, and 3. 4 and 3 is 7. And then to the last one, 0, 5, 0, 2, 5 and 2 is 7. So it's another 7 down here. Okay? So that multiplication wasn't too bad. But now let's think about this as if we partition the matrices, which is already partitioned for us. So if we redo this example where the matrices have been partitioned, and we'll call this, maybe we'll call this A1, A2, B11, B12, B21, B22. If this thing's partitioned correctly enough, we can expect our result here, if we multiply A and B, to be just like, pretend that these are elements themselves. So this is A1 times B11 plus A2 times B21, right? It's like taking this row and multiplying by this column. And then we'll do the same thing with taking that row and multiplying by the second column. And then that would be another column. It would be A1, B12 plus A2, B22. That looks a little more complicated, but let's see how much more complicated it would be. So we have A1, which is a 2 by 2, and B11, which is a 2 by 1. So what would we expect this to be when we do the multiplication? It's a what? It's a 2 by 1, right? So this better be the same size, a 2 by 1. So let's do the multiplication. So this matrix, the A1 matrix, times the B11 matrix, which is 0. So it's a 2 by 1, and it's 0. So I could just, without doing any calculations, I know that that's going to be the 0 matrix. And then I have A1 times B21, so it's this thing. So this is a smaller multiplication. I have 2 times 1 and 3 times negative 2. So it's 2 minus 6. What is that? Negative 4. And then I go down to the next one. 4 times 1, and then 5 times negative 2. So 1 minus 10, 9. Uh-oh, that doesn't look like. What? I'm doing 8, 2. Oh, yeah, sorry. Messed that one up. All right, so we're doing A2 times B21. This is the identity matrix, so anything times that, it's going to be itself, right? And I'm multiplying it by 1, negative 2. So because I know that this is the identity matrix, when I multiply A2 times B21, I'm just going to get whatever B21 was. That looks better. I was a little worried. So this first part is going to be 1, negative 2. Okay? All right, now let's take A1 and multiply it with B12, and that's this matrix over here, which is an identity matrix. So A1 times B12, that's just going to be 2, 3, 4, 5, right? Because I'm multiplying A1 times identity matrix. So maybe this would have helped a little bit, huh? B11 was a 0 matrix. A1 or A2 is identity matrix. This is A2's identity matrix. And it turns out that B12 is also the identity matrix. So all these identity matrices will help in the multiplication if we partition it properly. Okay, back to our actual multiplication. Our last thing that we need to find is A2, which is the identity matrix, times B22, which is this matrix over here. So I'm just going to write down the matrix. 5, 4, 3, 2. And so if we add this, this is just addition of matrices. 2 plus 5 is 7. 3 plus 4 is 7. 4 plus 3 is 7. 5 plus 2 is 7. So I don't know if that was any easier than doing this, but imagine now an even larger matrix where a good portion of it are zeros or ones, identity matrix. Then this might make some of your calculations a little bit easier. So that was kind of neat in terms of partitioning, or a good reason for partitioning a matrix is that when you multiply partitions and then you have some of your partitions include identities, zeros, and things like that, it makes your multiplication a little bit easier. Okay? All right, let's move on to another partitioning. This partitioning is really just partitioning by columns or by rows. And also looking at products. So here we have A is an m by n matrix and B is an n by r matrix. So we're looking at the product itself. We're multiplying it out. And they say that AB can be written as A times the partition of all these B matrices. So if we look at these matrices, we can look at them as a matrix column representation of the product. And what they're doing here is they're looking at A as a whole matrix and B as the column representation of the matrix. The same thing happens over here where you partition A into the row matrices, and then A times B is called the row times the matrix representation. Okay? So it looks a little confusing, and to tell you the truth, I've never really seen this work in real life, but I thought it was kind of interesting. So let's take a look at doing an example of this. All right, so here are your two matrices A, B, and then we want to multiply them out. So instead of just multiplying it out, let's see if we can use a matrix column representation. Which one was that? Oh, here. So AB, we want to write AB instead of just writing the product itself. We want to write AB as a linear combination of the columns of A. So what we're going to do is we're going to break A into these columns. And then each of those columns will be multiplied by the matrix B. So if we take a look at the process again, so this is a matrix column representation. Oh, I'm sorry, we're going to break up B. Is that what we're going to do? Linear combinations of columns of A. I think they meant columns of B. What? No, columns of B. Yeah, so what they're doing in this one, the matrix column representation, A is a whole matrix that you're going to take, and then you're going to take a look at No, these are column vectors. If you look at B, you're going to look at B as breaking up the columns. All right, let's see if we can. I have a question about this, but let's see if we could do it. AB is equal to the matrix A times each of these as vectors separately, done separately. So 2, 1, negative 1, 3, minus 1, 6, 0, 1, 4. So what we want to do is we want to multiply A times 2, 1, negative 1. So A is a 3 by 3 matrix. B is a 3 by 1 matrix, right? So when we multiply that out, we should get a 3 by 1 matrix. So this is the first column. And then the second column is going to be A times 3 minus 1, 6. And then the third column is going to be A times 0, 1, 4. So those are the three columns of your product matrix. So what we want to do is we want to take a look at 1, negative 3, 2, 0, 1, 0, minus 2, 1, negative 1. This is your matrix A, and we want to multiply this by each of these vectors, column vectors. 2, 1, negative 1. So your first column will be 2, 0, positive 2, so that's 4. Your next row on that first column will be negative 6, plus 1, negative 5, minus 1, negative 6 again. And then four, 0, 4 plus 1 is 5. So you get 5. Okay. Linear combination of columns of A. All right, well, let's take a look at our next column. Which is going to be that same matrix A, this time being multiplied by 3 minus 1, 6. So we have a 3, 0, and negative 12. So that's negative 9. Negative 3 times 3 is negative 9, minus 1, negative 10, negative 10 plus 6, negative 4. And then 6, 0, minus 6, so looks like the last one's going to be 0. All right, so that's the second row, and then we could do one more. When we multiply this by the last column of B, and the last column of B is 0, 1, 4. So 0, 0, negative 2 times 4 is negative 8. We have a 0, 1 plus 4 is 5. And then a 0 and a 0 and a negative 4. Okay. All right. So if we kind of refrained from doing the multiplication and kept our product, there's an extra parentheses here, kept the product looking like this, where each column of the product is really just the matrix times each row from the second column, or each column from the second matrix, then we can see it written like this. Yeah.
So let's say you're shifting something, break it up into pieces to send somewhere. Each piece will be like a row vector, and
Yeah. Yeah, this could be something like that. Using this, you know what? Yeah, where you need a key. I think there's something more to this, but I'm not digging it right now. Homework. So this is the row, what do you call it? Oh, this one's, okay, so this is probably how it should be done. So this is the other one, the row matrix representation. So the row matrix representation goes like this. A times B, and then we want to cut up A into the different rows. A1, A2, well, this was only a three-dimensional, so A3, and then your matrix B. So these are the rows for A, A1, A2, and A3. Right? So what we want to do is we want to take, all right, now I'm a little confused about this B business. Yeah, so this is how it becomes. Oh. Yeah, I had a feeling that you just put each element of A there. So that this is each element of A, 1, 0, negative 2, negative 3, 1, 1. Minus 3, minus 2, minus 1, and those are just the elements of these. So A1, I don't know why it becomes a row though. So A1 is this first row of A, and that's going to get distributed with the row of, yeah. And it would be the transformation. Yeah, I think that's what they're trying to get at, because when you do the multiplication, we think about multiplying by a column of B, but when you do the column of B, you're multiplying by this thing. So this is your column of B. Well, let's see if that's right. It might be, yeah, it might be the transpose. So 1, 0, minus 2, 3, 1, 1, minus 3, minus 2, minus 1. So that looks okay. And then they just want you to do the calculations here. So this is 2, 3 minus 2, and then this whole thing is 0, and this is multiplied by negative 2. So negative 2 times negative 1 is positive 2. So you add that with a 2 in the first one, so that makes a 4. And then here you have 3, and then negative 2 times 6 is negative 12. So negative 12 plus 3, negative 9. And there's 0 here, so we're not counting the middle one. So we have negative 2 and 0, it's negative 2. And that should work. Okay, so those look good, and then we just need to fill in the rest of them. But I think your final answer is since these are the rows of AB, you actually since this is oh yeah, so it should still be the rows, right? Minus 9 and negative 2. Nope. Oh, yeah. Okay. Well, whatever happens. So, anyways, let's move on. Yeah, well, the problem will tell you the two matrices in the beginning, and then they would tell you whether you want a matrix column or a row matrix representation. And then they'll set it up like this. All right. Moving on. Powers, matrix powers. So for you to be able to take a power of a matrix, what you need is a square matrix, because you're multiplying it by itself. And so according to the matrix, the first matrix has to have the same, the number of columns in the first matrix has to have the same number of rows for the second matrix. So if you're taking something to the second power, then you have to have the same columns as the same rows, which forces you to have a square matrix. So this thing will only work for square matrices. If you imagine taking a 3 by 2 matrix and then squaring that, then you would multiply a 3 by 2 matrix with a 3 by 2 matrix, which will not work. So this idea of squaring it will only work for square matrices. So we've established a convention that anything to the 0 power is equal to 1 for our number system. So it turns out that for matrices it'll work also. except instead of 1, we have the identity matrix. And then we have to the second, to the third, etc. What we don't have is a negative power or a fractional power. So negative, remember, is like a reciprocal. So we'll define the idea of a reciprocal later. That might make sense for us. And then a fractional power is like a square root, where that wouldn't make sense for us yet either. But for now, let's just think about it as positive integers, including 0, with that special definition for 0. And so coming along with that are some basic properties, which is the same properties that we've seen for exponents for real numbers, and that is if you're multiplying a raised to the r power, a raised to the s power, it's the same thing as adding these things. So these aren't to be taken for granted because of the way our A's, our matrices work. And I want to give you an example of a property that we have for real numbers with powers that that we kind of use and take for granted. And there's this property for exponents where if you're multiplying something and you're taking that product to a power, it's like distributing the power, right? Seems obvious. So our example would be, what if we take A times B and raise that to the second power? And I have to say that this is not always going to be true. So we think about a product as a product that we're going to do inside of the parentheses, and then we'll eventually square that. Another way to think about this is that we take this product and then we're going to multiply it by itself again. Now, matrix multiplication could be associative, but it's not necessarily commutative. So saying that your product is A times B times A times B is not the same as A times B times B. In other words, the two middle matrices, B times A here, like to switch them around, but remember that matrix is not commutative, so you can't just switch A and B around. So there are restrictions to these properties that we take for granted for real numbers that we have to be a little bit more careful with when we're dealing with matrices. All right? Okay, along the same lines as the powers are a couple of matrices that are interesting. For this one, I was thinking about just using MATLAB or something, but let's do it by hand and see, get our matrix multiplication practice going. Let's do the first one. We have a special matrix, 1, 1, 1, 1. We're trying to see if we can find a pattern for this. To find a pattern for something, we'll start off by squaring it and take it to the third power and then see if we can figure it out. So the square of this, 1, 1, 1, 1, 1, 1, 1, 1. So 1 plus 1 is 2. 1 plus 1 is 2. 1 plus 1 is 2. Plus 1 is 2. Is that right? You guys should check. I see a pattern. What do you think a cubed is? 3, 3, 3, 3? Let's see. A cubed is, now we have to be careful about matrix multiplication, right? It's A times A times A. And then we can group either of these. So why don't we just group the second one, that's A squared, which we got from before. So A is 1, 1, 1, 1, and A squared is 2, 2, 2, 2. So this is 2, oh, it's 4. It's not 3. 4, 4, 4, 4. All right, let's refine our guess again. What's happening as we are taking this to a power? What? Is it doubling? Let's see. A to the fourth. A times A times A times A. Now I have A cubed, but I also have A squared, so I can just group 2 at a time. Or I can say 1, 1, 1, 1 times 4, 4, 4, 4. So either way would work. I think I'm going to say 2, 2, 2, 2 times 2, 2, 2, 2. That's A squared, right? Could have done this the other way also with 1, 1, 1, 1 times 4, 4, 4, 4. Either way it should come out to be the same. So the general idea is I want to find a pattern for AK. So what should AK equal to? AK is equal to what? It's all the same, right? So I would just pick one. Two to the K minus 1. And as long as we say that K is bigger than 1 or equal to 1, then we're all good. All right, that was a good pattern finding exercise. So there's a couple more over here. You can try to find a pattern for these things for the sines and cosines and with this special matrix and see what happens. All right, questions? Let's see what's next. Let's move on. One more definition in the section is a transpose, which we all probably know already. But here it's just a definition. Transpose of an M by N matrix is an N by N matrix. So the number of rows and number of columns switch. And all you do is essentially interchange the rows and columns. So you change the rows and columns, then you have the transpose. We've done this in MATLAB, and we did it with vectors, but you could certainly do it in matrices. Vectors are just like single row matrices. So if you remember in MATLAB, we defined a vector as 1, 2, 3. And then when you say a transpose, and in MATLAB we use an apostrophe for your transpose, this becomes a 1, 2, 3. So that's our transpose. So that works with, like I said, matrices or vectors. If you look at a row vector, it becomes a column vector, and vice versa. So along the lines of transposing, if you transpose a matrix and it looks just like the original matrix, then we say that that matrix is symmetric. So that's probably easy to visualize. You have 1, 2, 3, 4, 5, 6. And as long as this is 4, 5, 6 in the same place, then it would be symmetric. So a symmetric matrix doesn't matter what's in the diagonal, but across from the diagonal, you should have these numbers matching, so that if you take the transpose of it, you're going to get those same values there. Okay? So that's the deal with a symmetric matrix. And when they talk about symmetry, the symmetry is about the diagonal. It's like folding this matrix in half. And this obviously only works for square matrices, right? Because if you have a rectangular matrix and you try to find the symmetry about the diagonal, you're not going to see it. Okay, any questions? All right, I think that's the end of that section. There's a couple of definitions in the problem set that I hate it when books do that. I guess it's in the next section. They define what I think is an important concept, not in the body of the section, but they define it as a problem in the text. So we'll run into a couple of those and see how they work out. All right. The next section is talking about matrix algebra. So applying more, going a little bit beyond the addition and scalar multiplication that was kind of defined. Let's take a look at some properties of the arithmetic that we've been doing to these matrices. So what we have to assume here is we have to assume that the matrices are in that appropriate size so that you can add them. So they say that A, B, and C are matrices, all the same size, and little c and little d are scalars. So here we have addition is commutative. Multiplication is not, but addition fortunately is. It's also associative. There's I thought we did this already. Did we do this already? Seems like we did. This is all addition stuff. We did it with vectors, but we didn't do it with matrices. All right. So, this is all dealing with addition. Addition is commutative. Addition is associative. There is an additive identity called a zero identity. There's an additive inverse. This is distributive over scalar multiplication. So if we scalar multiply, it's distributive. It's also distributive with a matrix and then two scalars being added. It's associative when two scalars are involved. And this number 1 is not the identity matrix, but the actual number 1. Just the real number 1. I thought this would have been stuff that they would have discussed in the first section, but I guess not. Let me check something real quick. Oh, here's the multiplication properties. Okay, they're coming. All right, so these are the addition and scalar multiplication properties. And I guess we should try to see if there's any interesting problems to do that's associated with this stuff. Let's see. Solve. So you could pretend that this is just algebra and solve for it using the what do you call it? Addition property of equality or something. So let's do one of these. You want to do one or two? Number 2. So I have 3x is equal to a plus 2b. So I'm going to write the matrix out. A is 1, 2, 3, 4, plus 2b. B is minus 1, 0, 1, 1. So remember the x is a matrix. I don't know if you want to use a capital X, so I usually put a line on top and a line on bottom to consider it a capital X. So this is a matrix I'm looking for, not just a real number. So what we could do is we could simplify just like we would do in regular algebra, simplify this matrix. So this right-hand side will be 1 minus 2, or 1 plus negative 2, 2 plus 0, 3 plus 2, and 4 plus 2. Is that right? Did I do that right? So I scalar multiplied this b vector and then added it to a. I should have been subtracting, huh? Nobody caught that. Try it again. 1 plus 2 is 3. 2, that's still going to be a 2. 3 minus 2 is 1. 4 minus 2 is 2. Is that better? All right. Now, the other thing we could do is divide by 3 on both sides. Dividing by 3 is probably better seen and with matrix multiplication as multiplying by 1/3. And so you could just, one of the properties that they had that we talked about in the last section was to multiply by scalar. You have to multiply every single element in that matrix. So here it goes. This should be your final answer for x. X is equal to this. All right, so that's just basic algebra, taking advantage of some of the properties that we were just discussing. All right, let's see if there's any other interesting problems we could do. Write as a linear combination of another matrix, if possible. Which one should we do for this one? 6 or 7 or 5 or 6? This is 5. Let's do 6. Let's do 6. There's 3 of them. Well, A's identity, this one is not quite the identity. And this one's just that. All right, let's see if we could do this. This is a little trickier. And this actually would lead us to doing another lights out game with instead of just a row of lights, we can have a matrix of lights. So what we want to do is we want to see if we can write B 2 minus 1 minus 3 2 as a linear combination of A1, A2, and A3. So linear combination means, remember, you have to see if you can write as scalar multiple of each of these added together. If that's at all possible. So that's what we're going to try to do. We're going to try to solve for alpha 1, alpha 2, and alpha 3. Now, I think what I'm going to end up here is a bunch of equations, right? So what bunch of equations are we going to get? So this is alpha 1. How should we do this? I don't know if this is a waste of time, but I'm going to see if I can write it like this, see if it'll help out. So what we have to do is kind of attack it component by component. And so, for example, if we want this first slot here, the 2, that linear combination has to be satisfied with this equation. So we have alpha 1 plus 0 alpha 2 plus alpha 3 is equal to 2. And then the next slot, 0, and then we have an alpha 2 minus alpha 3 is equal to negative 1. And then now we go down to the 2 by 1 position to get negative 3 over here. So we're looking at 0, alpha 1, alpha 2 again, plus alpha 3 is equal to negative 3. And then finally that last slot, which is equal to 2, is going to be by alpha 1 plus 0 alpha 2 plus alpha 3. Okay. So we have 4 equations and 3 unknowns. What are our chances here? Are we going to get values for this? I hope so. Let's see. So we've translated our linear combination problem into a system of linear equations. And let's see, we got 1, 0, 1, 0, 1, negative 1, 0, 1, 1, 1, 0, 1. Those are the coefficients for my alphas. And then my augmented part is 2 minus 1 minus 3, 2. So let's see if we can row reduce this to get something going. It looks like the first and the last row is the same, right? So let's just say we added it, row 1 plus or minus row 1 plus row 3, or row 4, sorry, to eliminate that whole thing. But the row 2 and row 3 are a little bit different. So let's take row 2, multiply it by negative 1, and add it to row 3. Oh, row 3, yeah. Row 3, yeah. And then let's replace that. So the first row doesn't change. The second row will not change. So this is what's going to change. It's going to change to a 0 here. And negative 1 times negative 1 is positive 1. Add it to this is positive 2. Negative 1 is positive 1. Add to negative 3 is negative 2. So I think I'm good with this. Let's not completely reduce row echelon it. Let's just stop here and then do some backward solving here. So this is alpha 2 or alpha 3. 2 alpha 3 is equal to negative 2, which means alpha 3 is equal to negative 1. Right? The next one is alpha 2 minus alpha 3 is equal to negative 1. Alpha 3 is negative 1. Alpha 2 minus negative 1 is equal to negative 1. So alpha 2 is equal to negative 2. And then finally, we got alpha 1 plus alpha 3 is equal to 2. That's alpha 1 plus alpha 3 is negative 1 is equal to 2. So alpha 3 is alpha 1 is 3. So we got 3, negative 2, negative 1. And if you put 3, negative 2, and negative 1 for these alphas, and then perform the calculations, you should see it come out. Okay, this is almost, this is very similar to linear combination stuff that we've been doing, except instead of vectors, we're dealing with matrices, right? So if you carefully look at the coefficients, look at the system that we have, and look at the, for example, the first row. It's 1, 0, 0, 1. So it's 1, 0, 0, 1 in the order that we have the matrix written by rows. So it's not a coincidence that it turns out like that. The second one is 0, 1, 1, 0, right? 0, 1, 1, 0, and the last one is negative 1, or sorry, positive 1, negative 1, 1, and 1. So positive 1, negative 1, 1, and 1. So those are the coefficients of these things. So we're kind of looking at a matrix and expanding it to make it look like a vector and doing what we've been doing all along. All right, that was, yeah. I was going to say it was fun, but it wasn't really that fun. Yeah?
Do a linear combination by the row matrix forms. So where we have the row for the matrix in A1, A2, A3.
Uh-huh.
The rows would be 1, 2, 0, 1 would be the matrix.
Well, that only works if you're multiplying the matrices together. So, in this case, we're not doing any matrix multiplication. Okay. Span. Should we look at the span? Span of A1 and A2. Let's take a look at the span of A1 and A2. We did 5 or 6? We did 6. Span of A1, A2, and A3. So we're going to ignore B. Well, we could ignore B, or we can look at it. So we have these three matrices here, A1, A2, and A3, and we're interested in finding the span of them. So what is a span of a bunch of matrices? Well, the span of a bunch of matrices will be a whole collection, a whole set of matrices that fall into the linear combination of them. So basically, the span of A1, A2, A3, if we take a look at that, use the same definition, is equal to any matrix of the form. So basically, put alphas in front of them of the form alpha 1, A1 plus alpha 2, A2 plus alpha 3, A3. See if we could take a closer look at that. If I multiply each of them by alpha 1, alpha 2, alpha 3, and then I added them, so I would have alpha 1 plus 0, alpha 2 plus alpha 3. I would have 0 times alpha 1, alpha 2 minus alpha 3. And then I would have 0 for alpha 1, alpha 2 plus alpha 3. And then alpha 1 and 0 for alpha 2 and then alpha 3. So the span of this matrix would be any matrix that would look like this for different alpha 1, alpha 2s, and alpha 3s. So you can randomly pick numbers for alpha 1, alpha 2, and alpha 3, and then plop them in here, and then you'll get a matrix in the span. There are no zeros or no ones or no actual numbers that would just come out of here, so it doesn't look like we're going to come out with anything more than just matrix of this form kind of business. Doesn't look like it's symmetric either. It looks like the diagonal looks like it's going to be the same, right? It's alpha 1 plus alpha 3. And then the opposites look like it's a little bit different. But it's off by, adding or subtracting the same number to a number. So let's see if we can make up a matrix in this span. So let's call it C. I can randomly pick any number. Give me a number. 5. So as long as the diagonal is the same, right? And then now I have to have restrictions on the wings also. So give me two numbers for this. 4 and 3. So 4 plus 3 is 7. 4 minus 3 is positive 1. So here is an example of this, which is in the span of this matrix. So if we were to figure, instead of B, which is what we found in the last one, B is in the span of this, which means we can find alpha 1, alpha 2, and alpha 3 that would make this fit. Now, I could do the same thing for C, and I'll have different alphas that would write this as a linear combination of A1, A2, and A3. Okay? So that's what it means to be in a span. All right. It's 2 o'clock. I don't know. You guys want your exams or no? I suppose I should give it to you.